Hello, ladies and gentlemen. Thanks so much for coming. First off, full disclosure, I'm going to go through a use case, and that is not something that's clinical advice or anything like that. It's something that is very dear to my heart, but there's a lot of ethics and stuff that I'm going to breeze over, and I just don't want people to take it as something that it's not. Really, this is a technology-focused talk about core problems. With that, I don't know if you guys have heard of David Hilbert. Is a very famous mathematician that proposed some mathematics problems around the turn of the century. And today I'm going to talk about personalized medicine problems. And Spark is awesome at solving a lot of them, either Spark and another technology or Spark just by itself. So let me talk about the personal story a little bit first. This goes back to around 2003 when I met this person in the middle here. He's actually on a big Coker unicycle riding across Iowa. I don't know if you know very many people that ride across Iowa on a unicycle, but it's fair to say that this is a very dynamic and interesting person, and his name's Jesse Shoemaker. We actually started the Gravity Works Jugglers and did all kinds of crazy things together right out of college, such as juggling fire and exploding ourselves, etc. But things became a little bit more practical. Jesse got an MBA and went towards a really great career at Union Pacific Railroad, and I went into data science and bioinformatics. And this is not very long after. This is something that you probably can all relate to. Jesse had a daughter, and her name's Maddie. And so this is Maddie's story. And I'll do Maddie's story within the context of personalized medicine and what it means. So Maddie's 8 years old when she was diagnosed with a really rare brain cancer, DIPG. There's only about 300 people in the world that are diagnosed with DIPG every year. But I think that it's not so unique in that probably every cancer is a little bit like DIPG in that it's its own disease, right? So Maddie was diagnosed, and Jesse was just totally devastated at the time. And I was working at the time in the Center for Individualized Medicine at Mayo Clinic, and I was talking to him about some things, and he was looking at a lot of different treatment options. This is sort of the cascade of things that happened before she passed away on December 10th. One of the things that happened was that Sloan Kettering, this is where DIPG tumors sit. Sloan Kettering actually did a very innovative technique to get a biopsy of this tumor before she passed away. And they generated, there was actually Giselle Schroller's lab in Michigan generated 3 different kinds of data for this specific patient. There's whole genome, that's a whole exome data, that means only the genes in the genome. For the cancer itself, the cancer cells, and Maddie herself, RNA-seq, and then there's drug-gene interaction articles as well. So that was available for the tumor board. So if you guys don't know what a tumor board is, typically the tumor board takes the inputs from this, this huge pipeline, right? There's all this data flowing. This is what SparkConf is all about, right? So you take all this data, you whittle it down into basically PDF documents or Excel spreadsheets that the tumor board then has access to at the time of treatment. So the first part of this large pipeline, which I call problem number 1, is just doing the variant calling. And I'm not an expert in the variant calling methodologies. I think there's going to be some good talks later about variant calling and what that is. But it basically takes all those raw ATG reads and then maps them to the genome. And then you can call variants or deltas based on the pileup that you see. Yeah, so do I have a mouse? No, I don't have. Oh, I do have a mouse. Good. So so this is the pileup right here. As you map those reads to the genome at a given location, you'll see differences or deltas. And those differences are the variants in an individual. Now, one of the problems with the variant set, it's quite large. For example, here we see it's a whole exome, so it's only 62,000. In the case of whole genome, it's 3 to 5 million. So that's quite a bit of data. But then you're doing this for many different patients. But we don't know what those things do. So there's surveys, for example, the 1,000 Genome Survey, that will go and look at what happens naturally in the population. Is this variant a variant because it's, you're African American or you're Caucasian, or is this a variant that is causative in the cancer, right? That's kind of one of the big, huge questions that we have. So one of the things with annotation is being able to synthesize all these different data types together. It's kind of like labeling a city. And these are the kind of different data types that we're interested in here. For example, genome pathways, the surveys, for example, 1,000 genomes, drug-gene interactions, or specific drug-SNP interactions. Then we're also interested in regulatory networks, et cetera, et cetera. And we actually have an annotation engine. It's called BioR. It's a terrible name, but it just kind of happened. Anyway, in any case, what that annotation engine does is it takes the raw data. For example, here would be the original raw data, and then it will synthesize that raw data with the added data from the annotation source. For example, if you want to know where the genes are in that raw VCF data that comes in, we convert that into JSON, and then we tack the genes based on what overlaps onto the end. And so that's the overall process of annotation. It uses command line tools in combination with this basically joins that Spark is really good at, by the way, to do a data flow pipeline. And that data flow pipeline basically tacks additional annotations onto the end and remunges those data elements back into the original structure. So this is what you get when you do that merger. So this is on the left-hand side, you see the original call structure. In Maddie's case, for example, this would be sample 1 and sample 2 would be the her exome, and then the exome for the cancer itself. And you want to know if it's in cancer or in her. You want to do basically set operations, right? Plus all the different annotations. Is this common in the population, or is this, so not deleterious from a tool like SNP effect, et cetera. And so what genetic counselors will do is they'll actually sit down in front of a computer and interactively query this data, right, to try to figure out. And it's very, very specific based on the use case that you're looking at right now. Is it a rare disease, or is it cancer, et cetera, et cetera? So based on what they're looking at, they'll actually be able to filter down into the specifics for that patient to find those variants of interest. And so we have a tool that you can download for free. It's based on MongoDB, but I can see Spark being able to address that as well. In Maddie's case, this is the kind of thing you do. You start with 61,000 some odd variants. And again, in whole genome, you got 3 to 5 million variants. And then you can look at those things that are in the germline versus the somatic. You can look at, only those things that are SNP effect, high impact, and cancer-causing genes, et cetera. And so when you look at what was available for the tumor board in her case, there's 83 things filtered automatically by this tool called Anavar. So that's what I would call like a peg down pipeline. Whereas at VCF Miner, you could look at it multiple different ways, and you could filter so that you could get, only in the cancer genes from Cosmic and, for example, damaging as predicted by SNP effect, right? So you could do that kind of query very easily. And it's interesting because when you look at a case like this, you see things that are in the literature, and that's purple, that are not in the clinical report, for example. And you can see things that are in the clinical report, of course, that were treated at the time of diagnosis. And then you can also see novel things that we can find by filtering the data in slightly different things. So there's a lot of data there that we can act upon that we don't necessarily act upon at the time of treatment. And so the reason I'll get to in a little bit is that sometimes we don't know what those variants mean, and we don't know how to target them with drugs. So let me just get into that idea right now a little bit deeper. So this is what I call problem 4, which is clinical oncology. So basically what I'm saying here is when I've treated a patient in the past, what did I do, right? Can I store that in a database? That's not necessarily a big data problem, but it's a really important problem, right? Because if I know what the care paths were in the past, then I can choose to improve things or change it up a little bit, or direct my research towards choosing better care paths in the future. So this is an example of how a clinical report would look. They reduced that overall amount of information down to just, in this case, a few SNPs, and then they also have RNA-seq, which I'll get into in a second, and then there's also, you know, for example, a drug or SNP drug interactions, right? And then the tumor board themselves is a committee of experts that will then decide what treatment is based on the information presented to them. So back to the RNA-seq, one of the things that's really specific in her case, and I don't know how many institutions are doing this throughout the United States. In this case, it's under an IRB and it's in a clinical trial, so it's not the standard of care for everybody that goes through personalized medicine. But in her case, she did get RNA-seq as well. And that data reads out basically as a reads per kilobase mapped sort of plot. And it's really important to understand if there's expression or if there's not expression, because in some diseases you can actually have a SNP or deleterious SNP predicted in a really important gene, but yet, because you know you've got two chromosomes, right? So one of those chromosomes could have the deleterious SNP, but the other one could look okay. But then if there's no expression on that one, then that one's actually knocked down as well. So you'll get the you know, deleterious behavior. So this data is very important to integrate, but I don't think that there's very many clinical pipelines that are doing it right now. And that brings me to one other data source that's really, really important, and that is the metadata. And there's multiple ways within an institution that you can pull together metadata. One of those ways is to have you know, study coordinators go out and collect the data from the different patients themselves, look at the medical record, and just basically put it into a specialized database. And another way is to use natural language processing. And that sounds a little bit strange, but the reality is that a lot of these diagnostic codes are not very good. Like SNOMED codes and stuff are not very good at saying, oh, hey, Maddie has DIPG, for example. That will be in the clinical report written out. So you need to actually parse those clinical reports to find that information. But once you do, you can start to look at groups of patients. And so back to the topic of the talk, that's what I'm considering N+1. So let me describe this, and if you've got questions, you can ask me later. But basically, this is the crux of it. I can treat patient N, but I have limited amount of data when I'm treating patient N. It really matters what the previous N cases were, right? The previous N cases with the same diagnostic situation. Because if I have all that information at the time of treatment, then I can improve N+1's care. And that's really the heart of it, right? So let me describe N again, just so that you guys can, this is kind of one pipeline. It's not the only pipeline out there. There's a lot of people doing this kind of work. You know, sequencing goes through primary analysis where you map the reads, then you call variants, then you may want to store those variants in some sort of large data warehouse of the previous N patients. Then you've got to synthesize that data from the metadata itself, right? And then you annotate those variants of interest, and then you can sort and filter those things. And this doesn't have to go in a specific order. Typically, you know, obviously you've got to do primary analysis before you can do variant calling, but in general, a lot of these things can feed back on each other. And so when you talk about N+1, you know, you're saying, okay, well, here's Maddie, for example. Now let's identify people with similar features to her. And you could do that from the clinical records, or you could do it even based on SNPs, right? And let's find people that are not like her, right, but are reasonable. And so you can do basically a cohort analysis with cases and controls, right? And you want to find those group in the cases are different from those in the controls. That's the kind of analysis. And traditionally what we would do when you do this kind of thing is that you do a SQL query in some relational database, right, that has this, like the EMR, right, would have some of this data. But it's very limited, right? And you want to be able to compare people based on similar pathways, for example. That's not going to be in the EMR. Or similar genes that are expressed, etc. And so really, I think you could actually build a better cohort analysis by kind of synthesizing these things together, both the phenotype and the observations with genes and their specific mutations, upregulated, downregulated genes based on RNA-seq data, given pathways, and so on. And you could find cohorts that are really close. So that brings me to problem 8, which is dynamic recalculation. And let me describe what this is. When you have a pileup like this, there's different coverage between individuals. For example, some of the individuals in the cohort are going to have whole genome sequencing, whereas others will have only whole exome sequencing. So certain parts won't be covered. And when you do that, you have to recalculate, because you can't say that a SNP is there or not there, or it's important in one group because it's a null value, basically. It seems really trivial to database people. Oh yeah, nulls, store your nulls, right? But there's millions and millions of nulls in there. And so you've got to be able to calculate them accurately. And so let me go down here and just talk about how that works, right? In practice, you have to store the data for all the different VCFs, and then the GVCF has the coverage data as well. And then, for example, here, man, what is going on? I cannot see this thing. So anyway, here you have dots where where it's basically null, where I don't have coverage, right? So you say 0, 0, that's saying I've got coverage and it's not there. And you basically look at the list of those things in the GVCF versus what's in the VCF to figure out how to build this matrix. So that brings me back to my my 9th problem that I wanted to talk about today, which is about how you share data. And it seems like, oh yeah, this should be really easy, right? You just FTP it over to me or something like that. Or you know, we all join the same consortia. But in reality, it's hard, because when you're sharing someone's genome, you're actually sharing other things. For example, if I were to share Maddie's genome, or just put it out on the web or something, I'd actually be sharing Jesse's genome as well, at least half of it, right? And so that's kind of a problem. But in order to do something like solve rare disease, where there's only like 300 individuals in the United States per year, you have to actually bring data like this together to start to figure out what's causative. Because yeah, I can filter variants, as I showed you earlier, and I can find specific things in that data set, but it doesn't really mean anything because I don't have a large enough cohort of individuals to be able to say, is this causative, is this in this group, or is it not in that group? So I think that's a really big problem, and not necessarily one that we can solve here, but at least if we give people, I look at Spark and the big data stack as kind of like the honeypot, right? If you give everybody the good tools, then they'll just adopt that, and then sharing is easier than if it was just sort of everybody do it your own way. Oh yeah, that's really not working as for us, etc. So I think that's kind of the strategy I'd like to employ. So talking technology for just a little second here, I've done a lot of experiments. I'm happy to share code snippets and stuff on Spark. And we've done a lot of implementations in different languages. Right now, this thermometer thing is a technology readiness level. And I would assess the current technology readiness level of the big data stack towards addressing these kinds of problems at a 3. Let me make that kind of clear. 1 is basically, oh, this is a great idea, let's do it, right? And 9 is like, you know, Nimitz class aircraft carrier out there, you know, telling people what's what, right? And so what I'm saying is that we're kind of in early technology development in terms of, not in terms of the clinical production pipelines that we have, those are really good, but in terms of applying Spark in this space, because there's a lot of issues that we really have to address to make this stuff production grade. I think I'll leave everybody with an important note. There's a ride this summer for Maddie for DIPG, and Jesse's working on a lot of fundraising, and they need help from both technologists and people who are in the medical space to figure out what experiments we need to do to solve cases like this. And I don't know if you guys know the Facebook page. My wife is always talking to me about Facebook. There's this thing, Facebook, right? No, I'm just kidding. So, but anyway, there's a huge thing, Humans of New York on Facebook, that is looking into pediatric cancer. So I'd like to, with that, I'd like to put up my thanks and ask for any questions that you might have.
Let's give him a big hand. Questions?
I know your focus has mostly been analysis, but I have a couple infrastructure questions.
Yeah.
So I have a friend at the Nevada Institute of Personalized Medicine who's trying to do something similar. And one of the challenges has been around data security. So if you have a series of doctors looking at patient data, if you do a join on the variants versus that are in the genomes versus, say, the annotations of those variants, a doctor may see something that they don't have privilege to see. So they're looking at trying to identify like a row-level security model. Now, the best I've come up with so far is you store each variant in a separate JSON object and then in some sort of object store with an access control list. So you only pull in the rows they can see. Have you guys had to face that issue, and have you come up with a better solution?
That's an excellent question. Yes, we absolutely have to face that issue. Yes, it is very important. And yes, it's very real. So row-level locking, yeah, we've tried that. I think Oracle actually has a product, their TRC, that works okay at whole exome scale for dealing with row-level security for those things. I think in general, the approach that I've tried to take instead is to say, okay, can we define a larger concept, like for example, a file-level concept of the cohort set that you want access to, and then give you access to everything in that group as opposed to individual row-level operations, because that's in some ways easier, because you can say, I want to do this study or whatever, I want to do this sort of analysis, or I want to be able to help this patient right now. And a lot of times, especially in a retrospective, that's really easy to get through an IRB, but with regard to security in general, I think it's very dangerous to put all the data in one big, huge data bucket. I think it really needs at least per patient level access control. And so in my mind, it's going to be a lot better if you can filter and sort the data on the fly for that individual case that you're trying to solve, because at that moment, you'll know the access control that you need. For us, typically, it's not a big deal for doctors, specifically MDs, because they're usually using those tools with that purpose. It's more of a problem with researchers who don't want to share their data with one another.
Okay, so in a follow-up question to this is, are your doctors or researchers using, say, SQL interfaces directly? Because you might be able to solve some of these challenges at, say, application level by having a column that's a list of users that can see certain data or something like that. What's sort of been the interaction? At what point have they been interacting with the system, I guess?
That's fascinating. I think right now, our genetic counselors typically use graphical user interfaces of one sort or another, and it needs to be pretty simple. I mean, just think about it from the perspective of if you've got a panel of doctors talking about a given case, that panel of doctors really, maybe they could say, oh, hey, I know about this drug, this worked well for this patient, does that make sense here? And then you need to be able to go click, click, right, and get the answer back pretty rapidly. And having somebody who's sort of a data munging expert at the table is sometimes helpful, but I know if I was there, I would be like, oh, I forget the table, what's the table name, blah, blah. And that's unacceptable in a clinical setting. So I think that higher level abstractions is what those guys want, but there's no doubt that genomics is going to go the direction of radiology, where you've got experts that really know that data type in the future that are helping the oncologist and whoever else to treat people directly.
Cool. Other questions?
Yeah, my name is Bruno. Question on the cohort identification. What specific techniques or models are you using for cohort identifications? And also, like, you you said that you're fusing a lot of features together. Are there some set of features that are much more dominant when you're doing these cohort identifications?
So are you talking about, for example, annotation features?
Yeah, you mentioned pathways, gene expressions, and like you're fusing a bunch of things together.
Yeah, so in the annotation engine, just hold the mic for a second. I need you to repeat the first part for me.
Oh,
so
okay.
in the annotation engine, we fuse features, and gene, specifically SNP effect gene, is really, really good. It really helps narrow down the space quite rapidly and gives good results. You know, so that's an example of something. Another thing, now in rare disease, OMIM is a good one as well. But again, it depends, right? In cancer, the cosmic gene census is going to be a more powerful data source than in rare disease, where OMIM is a more powerful data source. So our strategy in general is to just take all the variants that we have, that is sort of, it's growing, right? But it starts to plateau off because you know, patients have repetitive variants, right? And so as it starts to plateau off, you can just annotate that set, and you can annotate that set of variants with basically all the columns. Right now we use like 80 different columns from, I think, 30 or 40 different data sources. And you can actually download all those data sources that we have. We've got more up-to-date stuff internally, but you know, I think for us it was really about semantically integrating the data first, meaning this feature belongs in this part of the genome, sort of thing. So those genome coordinate-based queries are absolutely essential in getting that kind of thing to fly. So cohort analysis, right?
Yeah.
Yeah.
So the first part was just what sort of models or techniques or algorithms do you use for cohort analysis?
So to me, cohort analysis is something that is still in the future. We've done some preliminary things, and most of what we've done is based on SQL at this moment. That's not to say that things, so what I put in the slide deck was more futuristic and where we want to go. Ideally, we want to go towards machine learning and encoding features and basically being able to automatically discriminate those people who are really close based on multiple different data modalities rather than just, but we haven't actually worked out a pipeline that's functioning right now. Again, it's really kind of a SQL sort of thing. Yeah.
Cool, we have time for one more question. Nope. All right, let's give Daniel a big hand.